Well, we've seen oxidation of alcohols. We've seen how to convert alcohols into good leaving groups. And let's take a look at reduction of alcohols. So there's an old method that we used to do this, and that was taking an alcohol and using concentrated sulfuric acid to make an alkene, right, with low concentration of water. That's what that means. And then using H2 and platinum to make the alkane. Recall that through this mechanism, I might just do a little dot, 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 dot down here, that you end up forming a carbocation, right? So we'll just say carbocation forms like in the mechanism. Why is that important? Well, you are prone to rearrangements when carbocations form. So often we tend to try to avoid that because of forming unwanted side products. So here's our new method. It's just another kind of tool to put in the shed for multi-step synthesis, and that is that we tosylate. So TSCl, and then let's add here to make this really nice, right, pyridine. That'll make your tosylate ester here. And then we can use LiAlH4, right, also known as LAH, to undergo an SN2 type of a reaction in which we form an alkene. So there it is. It's just another thing that we can do, another trick that we can do if we want to make an alkane from an alcohol. Okay, so the next section, really there's just one more section really, is the conversion of alcohols to alkyl halides. And we'll see that there's a handful of methods that we can use to carry out this transformation. The first one is something we've actually already seen. So using HBr. So the idea is that you're taking this type of an alcohol, you're adding H plus to it, right? So you got something like HBr to it, and you end up getting SN1 and our SN2 product. So which type of reaction pathway we get, it depends entirely on what type of alcohol that you're dealing with first. So let's take a look at the reaction down here below of tertiary first. So I put this in here so we can go through it a little bit faster and you can take a break from writing stuff down. So, but we're going to put in arrows and stuff. So let's put in our lone pair here. So this is a tertiary alcohol, just to make sure we are all on the same page here. And the first step that would happen in this situation is that, and that's just a line right there, it's not a dash. The first thing that would happen here is we're going to come around and we're going to grab an H. So we're going to do this. So that'll make our OH2+. And because we're tertiary, we have the capability of just kicking that off. So here's our, right, that's your loss of water, right? And then you get this carbocation. Now we enter the realm of chapter 6 again, and this is just substitution stuff. So remember, little quiz, hybridization of that is, if you said sp2, you're correct. Now remember that that bromide can come in the front lobe. If it comes in the front lobe, right, and reacts with the p orbital of the sp2 hybridized atom, then the bromo group will be on a wedge. If the bromide comes around back and reacts at the back lobe of that carbon atom, then it'll be on a dash. So we get a mixture of those two products. Now, these are our SN1 products. Quick question, what's the relationship between the two? If you said they're diastereomers, you are indeed correct. All right, so that's our tertiary alcohols. Now let's take a look at secondary alcohols down here below. So secondary, you're going to see something that maybe is a little bit surprising for you here, but let's look at the reaction in a little bit of detail. So for secondary alcohols, let's put our lone pairs in. Right? We're still going to carry out that same first step, make that line not dashed between the H and the Br. And we're going to get this fellow here. Now, what I want to do is I want to take that and I want to continue the thought process up here and then also down below. All right, now when we do that, we can get a mixture of products. So let's just say up here, right, for secondary, let's just say this is SN2. So for SN2, right, we have bromide hanging out here. So then what's going to happen? Well, remember, your H is pointing out at you, right? And the OH2 here is your leaving group. So you're having to come around the front, which will cause an inversion to occur. So nothing's happening there, right? But that H is going to get pushed backwards. And you're going to be left with a bromo group pointing out here in the front. Okay, now if you're doing the SN1 route, well, what would form is this planar carbocation. And just like up above, then bromide can come front, right, or it can go back. So we can measure the differences here, sometimes using optical rotation. We'll talk about that in just a second, but we end up getting these two guys. So if you just kind of cover up that SN2 up above, like if you just forget about that guy, forget that that happens. If this was the only thing that occurred, then we would get a close to racemic mixture, right? Remember, it's not perfectly racemic, but it'd be close. Now, if SN2 also occurred, then we'd have a little bit more of this than maybe expected, right? Because you double dip it, you get it twice. And that's what you kind of find. So that's why you get a mixture of SN1 and SN2 here. All right. Now, what about primary? So primary is interesting, but that's going to proceed mostly by SN2. It's not going to be SN1, right? So I kind of didn't account for space here, so let's see if we can squeeze it in. So if you add that with HBr, you do this. So there's your H plus, right? And then you go through here, right, with bromide coming in. So bromide would swing around, and we would do this. So you get your bromo group there, right, plus your water. So that's going to be SN2 for us here. All right. So let's take a look at the next reaction here too. So this reagent is HCl, so hydrochloric acid, and zinc chloride, and it has a common name. It's called the Lucas reagent. So sometimes in second semester we do this experiment called qualitative analysis, and we use the Lucas reagent to help us determine whether or not we have a primary, secondary, or a tertiary alcohol. Okay, so let's look at the reaction here, and then we'll come back and hit some of these points up above in just a second. All right, so secondary and tertiary alcohol. So the mechanism proceeds through SN1. All right, so let's take a look at the mechanism here, and let's put in some electrons, and let's show the flow here. So what happens is these electrons are going to come over and make a bond with the zinc. And then you're going to form this charged intermediate complex. So let's put on our lone pair right there, circle that charge. Right, so then what happens is this whole zinc hydroxide chloride compound thing just leaves. Right? So put a circle around that guy up here. You get your carbocation, right? And with that, you're going to have an SN1 type of a reaction there, right? So 1, 2, 3, 4. That'd put your chloro there, or it would put your chloro here. And often these guys, they PPT out of our solution. So you can tell that there's a secondary alcohol or a tertiary present because you see a PPT, right? Now, because it's an SN1, secondary, tertiary are going to be good substrates, right? So tertiary, nice, because it forms a tertiary carbocation. Secondary, slower. So basically, if you carry this test out, you add the reagents all at the same time, and you go ahead and you hit your timer, and you kind of see how long it takes for your unknown to react, for example. So for primary alcohols, sometimes I even say don't even worry about this for the mechanism, but this is a slow reaction. It says greater than 6 minutes, but when you look this thing up, it can be like an hour, or I could say leave overnight, for example. So let's look at this reaction with a primary alcohol here. So why don't we take something like this, all right? And let's add to that our ZnCl2 here. So as we go through and do that, we're going to end up having to add some heat for this to occur. Now remember ZnCl2, let's put the N in there. This thing's a Lewis acid. So ZnCl2, this guy is a Lewis acid. The oxygen's the base. It's going to come over and do this. So we will form an O and H, ZnCl2, plus and a minus. Now SN1 reactions are faster than SN2 reactions. And this would lead to the formation of primary carbocation if it proceeded through SN1. So let's just do and say no SN1 because of primary carbocation. So that's why that's a slow reaction. So instead you just let it sit around, and it would proceed with an SN2. Again, a slower reaction, and then you would end up with your chloride on that thing. Sorry, you would end up with your chloride on there like this. Right? 1, 2, 3. Right, and then you would end up with 1, 2, 3, and your chloride right there, plus HOZnCl2 minus. A couple notes about this just here before we continue. This is a slow reaction, right? Because that SN2 is slower than SN1. And also because the reaction does not proceed via SN1.